I mean, you can easily process like millions of events per second. You can do that. I mean, it obviously depends on like how big your events are, right? If they're like 1 megabyte each, that might be a little bit tricky. But
hello everyone, welcome to the Geek Nator podcast. I am your host Kaivalya Apte, and in this series I'm talking to experts in our industry so we can get key insights from their experience and we can all learn together. Similarly, today I have a very interesting topic, which is distributed stream processing. And to talk about distributed stream processing, I have a software engineer, an expert in data intensive applications, and he's currently working as a principal engineer at Splunk. So with this, I want to welcome Max. Max, let's start with a bit of introduction.
Yeah, thanks for the intro, KV, and thanks for having me. As you mentioned, I'm a principal engineer at Splunk currently. I'm in this kind of field for some years. I initially started getting interested into concurrent and distributed applications during my master's studies in Berlin at university. And I went on to study at a research work at a research institute rather, and got involved into writing a transactional distributed key value store. Mm-hmm. And after I graduated, I went on to work on Apache Flink, rather the company behind Apache Flink. And through that, I got involved in open source development, very actively as a committer and project management committee member of the Flink project, Apache Flink project, and the Spark project. And I've been took some turns, but I sort of stayed in this realm of data, like distributed data processing and real-time stream processing. And this led me kind of where I am. So I'm curious I guess I have some, you mentioned I'm an expert. Yeah, I mean, we're all learning, of course, but I do have some knowledge about this space. So I'm curious to discuss stream processing topics today.
Awesome. Yeah. I'm actually looking forward to, our conversation on stream processing and, what I can learn and our audience can learn from your experience in stream processing and, kind of operating those stream processing pipelines into production and what kind of issues you faced and all those kind of things. So I'm really excited, and thanks a lot for joining. So with this, let's start with, like basics of stream processing. Like what exactly do we mean when we say like stream processing?
Yeah, that's a great question. And it's arguably, it's a little bit loaded of a question. These days, people talk about stream processing as it were a new thing, and it's always like batch and stream processing. That is, we get there in a second, but that's a kind of very coarse simplification. So what I want to do is maybe take a step back and see where does stream processing come from to understand this paradigm better. Yeah. So historically speaking, stream processing started in, I think, around the 80s in research. Back then, processing was strictly performed in this single instruction, single data model, and SysD, or I don't know how you pronounce this in English, but so basically it goes all the way back to this von Neumann architecture where you have a set of instructions and data, and you take an instruction and then you process some data and you repeat that all over again. Okay. That is a fine model and nothing wrong with it. But so people were looking in the 80s and research on how to apply more, or basically process more than a single piece of data with an instruction. And why is that necessary? Well, it is necessary because it's simply faster to run. If you can run an operation on a stream or a sequence of data, then you end up processing more data at once, and that's faster. How does this tie back to today's discussion about modern stream processors? Well, it's an old concept that is even present, before Flink or Kafka or Spark. You can find it on CPUs or more often on graphics card. But when we today talk about this stream processing, most people means distributed stream processing. Yeah. And that is not like locally in your GPU, but that's like multiple machines communicating over a network and processing a continuous stream of data.
Yeah.
So most commonly, this is a fleet of machines, because I think it became clear that it's too expensive to build like a supercomputer. But instead, we can leverage some of the properties of stream processing to use lots of small machines to process or divide the stream and process it. I think this. So to define stream processing more clearly, it's a principle that works if you have a stream that fulfills certain properties. So first property would be volume. It's not strictly necessary, but if you have a very tiny amount of data, there's not so much value in using stream processing. So mostly you have a lot of data and like not a lot of specialized computation on it. And then the second property is that your data is parallelizable, so it can be split and processed in parallel. You don't need to wait on one piece of data to be processed before you process the next one. And then there's some properties like data locality as well. So obviously, when you divide a stream, like you want to be able to process a part of a stream, apply multiple operations without like needing to like sync in between, like redistribute. We have that as well in stream processing. That's called shuffling. But if you shuffle all the time, that's kind of slow and not very efficient. So you want to be able to do local computation when possible. That's I think that was a long rant, but I hope that makes sense.
I mean, it's the topic itself is very vast, and there are so many things, but I think you covered it very nicely, and you covered like different parts like data locality and why is it important. Like if you do a lot of shuffling, what can go wrong? But I think we'll cover it in a bit later section. Coming back to like stream processing, like how is it different from like batch processing, for example?
Again, we could go back there and see that batch processing wasn't so much contrasted with stream processing in the early days, because batch processing was actually just as a way to run more than or multiple programs in sequence. So there was this problem that people had access to a terminal, but the terminal could only be used by one person at a time. So somebody came up with a way to basically batch different jobs of different people and process them one after another, and so that you wouldn't have to have exclusive access to a terminal to run some computation. Instead, you would submit your job, and then it would be ready at some later point in time. So that's where it comes from. I was interested in historical context. But today, of course, it means that rather than like real-time process data as it comes in, you sort of process it in batches. So that can mean like you collect everything in one place until, like, let's say you collect data for a day and then you run processing on it. But it can also mean even that you buffer data for short amounts of time, let's say for a couple seconds or for a minute or so, and then you do some processing on it. Batching is not. It's not that batching is bad and streaming is, better or something like that. It's also. I mean, it is more efficient if you have data lying around somewhere and you can process in a batch. It can be more efficient, right? Because you can just do it all at once and then you're done. With stream processing, it requires a continuous process to run, and sort of depending on the latency and throughputs you want, you have to decide how quickly you're going to react to data coming in. There's a trade-off, because if you want to react really fast, your throughput is probably not going to be very good because you can't buffer data. You run your execution immediately, which when computers process data, there's always some buffers involved. The smaller the buffers, the less data you will process at once. So that's some trade-off.
I think it makes sense. I mean, maybe it's like directly comparing batch processing and stream processing itself is kind of incorrect, or let's say incomplete, because I guess there is some batching at some level involved when we also do stream processing, right? Or
yes, there's inevitably some kind of batching involved. Because it's simply not feasible or too expensive to. It depends the answer. I guess it's not always feasible to process immediately. You want to do some kind of batching, but if you wait too long, you kind of lose the real-time aspect of streaming. So in Flink actually, and other systems I think as well, it's tunable. So you can set a buffer size, a network buffer size. So when the buffer is full, it triggers the complete computation. And in addition, you can also set a timer, basically. So you say don't wait longer than 1 second. If the buffer is not full, then already process the data, so we don't. So you have lower latency than if you were to wait.
Yeah. I think it makes sense. I think it's something similar in the Kafka world, like Kafka Stream world. But, you can always batch the number of records you're reading from a topic. But we'll come back to it, at a later stage when we try to compare these, different tools that are available. But before that, so I think you briefly covered, why do we need stream processing? But are there some requirements or some guarantees that we need to perform stream processing? Is it just that we want to be real time? Or it's also something different? Why has it become more relevant today, distributed stream processing?
That's a good question. Well, I think there's more data, and there's generally more machine or user generated data floating around, and there rises the need to have a system that can immediately take action upon those events or this data. If you and to some degree, this can even be more efficient, because you might be able to, let's say, reduce the volume of data immediately. Let's say you're only interested in a certain type of event that occurs very rarely, and you get a lot of other events, then it might make sense to immediately process these events, filter out what you need, save that somewhere, and as opposed to the batch way, which would be to write it all out to some file system S3, and then go over at a later point in time, which there might be some costs occurring for storing all these events, and it might be overall more efficient if you're looking for specific things. But of course, there's also use cases that are just impossible without stream processing. Let's say you want to monitor a fleet of deployments, and you want to generate an alert when something happens. Let's say when there's an intrusion, maybe, or when the machine breaks down or something like that. And for this to work on large scale, you'll need some kind of distributed stream processing. Yeah, if you don't have that much data, I mean, it might work to just use a bash script or, some Python program. But at some point, if there's just a lot of data and you want to perform some sophisticated analysis on it, and also recover in case of failures, and you rely on like correct behavior, then it makes sense to think about stream processor like Flink or Kafka Streams, Spark.
Yeah, sounds good. Just to summarize, whatever we discussed so far. So stream processing is when you have like a stream of data coming, or like a events stream coming, and you want to make some decisions very quickly on, in real time. And you have a lot of data. It's not like a very small amount of data. It's like really huge data. And you want to make quick decisions. Otherwise, those decisions do not make any sense. It's too late if it gets delayed. So I think that's when I would apply stream processing. Is that correct?
Yes, I'd say that is correct.
Okay, sounds good. Cool. So let's say I have this use case. I have lots of data. I have like stream of data coming in. So how do I do like stream processing? What are the tools available?
So potentially there are a lot of tools to do this job. Yeah, I mean, I'd say that to contrast stream processing stream event processing from typical, or from like event processing itself, I'd say that it's probably the data volume that you need some kind of. Well, I'd say, because you mentioned event processing, I think earlier. In sort of event processing, you take a look at each event that arrives and you make some decision. But these systems, especially the simple ones, are usually stateless. So they just have one or multiple workers and they do some sort of processing. Whereas stream event processing is a little bit more specialized in the sense that it can hold state and it can also recover from failures. And we get to correctnesses later on. But to answer your questions, what tools are out there? Well, I am mainly involved in the Apache space. So of course there's Apache Flink, there's Apache Kafka, or Kafka Streams rather. Then there's Spark, very well known processing tool which does batch and streaming. And there's also Apache Beam, which is sort of it's sort of an API that you can use independently of the execution engine, so you can run it on Flink, but also it's very well compatible with Google Cloud Dataflow and Spark as well. So these are main tools I know. Then of course, sort of maybe stream processors in the more specialized sense, like Apache Druid or Apache Pinot. But these are more, I guess, they're more time series oriented, almost. Well, they're not databases, but they're sort of a hybrid of stream processing and database. I guess it's similar to also how I would describe Elasticsearch. So they're not as general purpose in the sense that you can freely, you have all the flexibility of how your events are handled. It's rather like you build indexes and transformations it does feel like more databasey to me than like general purpose stream processors like Flink, Spark, Kafka.
Yeah, makes sense. Yeah, I think I have a little experience with Apache Pinot, and since you mentioned that, I see it more like a analytics data store, and it might be doing some stream processing to do those analysis and perform those analytics queries. But yeah, like someone like me, for example, like a developer, cannot use Apache Pinot for actually implementing stream processing. And as you mentioned, like there are different tools available to do this, like Apache Flink. There's Kafka Streaming and Spark Streaming, which use micro batching, I guess. And then there is Apache Beam. So I have very little experience in stream processing. I have experience in Kafka Streaming, but I haven't really used Flink and Beam in production setup. So how do they work? Like what are the like general components that are involved? Let's say if we talk about Flink.
Mm-hmm. Yeah. So the way this works is that you typically, from an end user perspective, you use the Flink API. It has a batch and a stream API, and you write a program that like logically defines your data flow. So you basically say read data from Kafka, and then apply this map function. Filter out some events, and when you're done with the processing, you write it to a sink. So a sink can be Kafka as well, or a message queue, a file, whatever. That's the kind of, so you end up with a data flow essentially. So when you've written this program in Flink, it's really convenient because you can test it locally. It sort of runs in your IDE, and it starts the components of Flink, which is the job manager, that's the master node, and a task manager, that's a worker. And that's kind of convenient. This feature is called mini cluster or local execution. So when you're set, and you can also write tests using that, so that's kind of nice. When you're done, when you're confident, then the way this typically works is that you build a jar. In Java words, you always build jars for everything. This jar, you submit this jar basically to the Flink cluster using Flink's REST API, and there it gets executed, and you end up with this DAG, so the execution plan, and then Flink ensures that the job manager, the master node, ensures that the necessary tasks extracted from this data flow get then run on the workers, the task managers. So it's kind of how it works. So if you want to deploy this, there are different ways. So you can deploy it sort of standalone on your machines, or you can run it on Kubernetes. So there's some integration with it. You have some options there to statically deploy it on Kubernetes, sort of a fixed cluster size, or you can even say like, create me more workers when necessary or something like that. So you have a lot of flexibility there, which is arguably also maybe the most complicated part of running Flink, because it has gotten easier, but there are a lot of knots and configuration. It's not only, it's probably true with a lot of open source tech, not only Flink. Same applies to Spark as well, and I believe Kafka. You need to know what you're doing there when you're running these systems in production. You do have like other dependencies as well. If you use the high availability feature, that requires Zookeeper as well. So the way this works is that to ensure that your that your cluster is doing the correct thing, and that only one master at a time is active only. There's a leader election taking place in Zookeeper, and that is the source of truth. And then there's also some Zookeeper is also used to store like checkpoint information, so it's sort of like the source of truth for what was the latest state of the system. So in case of failures, you are able to recover from that. So I guess that Zookeeper is not a strict dependency anymore. I mean, if you don't need HA, then anyways it is not. But there's also been some work to integrate it with the Kubernetes database, etcd. So you're not, because Zookeeper can be a pain to manage. So you're not strictly relying on this anymore. So, but I think the deployment model, maybe we should talk about how Kafka Streams is different than Flink, because with Flink, sort of you start your Flink cluster, then the Flink job runs there, so your data flow, and it sort of is able to interact with systems from the outside to read data or to write data. But when you were in the processing Flink handles everything for you. So for like sending data between the operators, shuffling data, and so on. This is a little bit of a different paradigm compared to how Kafka works. Kafka Streams. So Kafka is just a distributed log. It's just a storage for events. It's essentially a very good one, but that's all Kafka really is. But then you have Kafka Streams, which is sort of not, it's a different approach than Flink, because it's meant to be like a library, which you write a stream processing program on, and then you basically can just start it anywhere, and it just connects to Kafka, reads some data, and then writes data to Kafka. It's sort of, from a deployment perspective, much easier. That is, if you have, the catch is though, you need a Kafka cluster, right? And you have all the same problems with the Kafka cluster, of course, with Zookeeper. I heard they're getting rid of it, but you have all the same problems potentially with running a stable instance of Kafka. But but you're basically offloading your work to Kafka, and I think this is the nice part about Kafka Streams, but it's also kind of a disadvantage in my eyes, because while it's simpler operationally, you end up doing a lot of things that could be done natively in the stream processor. You end up like using Kafka, the Kafka log storage for doing that. For instance, when you do shuffling, Flink basically figures out how to shuffle data between the workers. Whereas Kafka uses Kafka topics. So it requires you to write your data to Kafka to be able to repartition, that is, to shuffle the data. I think that's, I guess that can be a lot slower and more resource heavy, I think, because every shuffle is going to force you to create a topic, and those topics need to be cleaned up and also compacted. But the beauty of it is that you just need Kafka, and you can start a process, and it pretty much just works, and that's pretty nice. Because like with Flink, you still need Kafka. You need some kind of message queue, so you end up maybe having more operational overhead. But at the same time, I think the scale is also much bigger with Flink. At least from my experience from talking with people using Kafka Streams, there are some scalability limitations. For most users, though, it should be fine, and it's probably the more approachable solution for stream processing.
Yeah, I think you covered so many interesting points. Like first is definitely the deployment model itself. So if we compare only Flink and Kafka Streams, so Kafka Streams, as you said, is like a embedded library. So you just need like a Kafka cluster, and if you have that cluster to connect to, and you can consume events. So it's like a simple Java application that you're running along with your application. And it still gives you all those programming constructs that you need for stream processing. So in that sense, it's really good. So if I have to put it differently, I don't have a lot of learning curve if I just wanted to get started with Kafka Streams, and if I know already like how to deal with Kafka. And as compared to Flink, you need some learning curve. You need like a Flink cluster to that is like operational and that can consume from some events. But then the second point is definitely you get much more features if you have like a Flink cluster. And the one bottleneck that you said it was about the scale is I think the Kafka streaming scale is kind of hard limited based on the topic that you're consuming. But maybe it can be even more distributed when we take it inside like a Flink cluster and not limited for the number of partition or Kafka topics. So I think I have also faced similar issues if I talk about Kafka Streams. But yeah, it's definitely easy to set up, easy to get started, and as you said, maybe if you are thinking about using Flink, you might as well have a dependency on Kafka cluster already, right? So what are those use cases? Like, so you talked about scale, like what kind of scale are we talking about here? So if I had to make a decision, like use Kafka Streams or Flink on the basis of scale, so what kind of scale have you seen, Flink easily support or, so how do we answer that question?
Yeah, that's a good question. So I've seen use cases where there were up to 1,000 nodes involved in a Flink cluster. I'm hearing that Alibaba, who uses Flink and develops Flink, has even scaled past that.
Yeah.
And in terms of the amount of data, so it's definitely in like, now I have to think how much actually, I mean, you can easily process like millions of events per second. You can do that. I mean, it obviously depends on like how big your events are, right? If they're like 1 megabyte each, that might be a little bit tricky, but, so, I mean, you can, I mean, even, at companies where I worked at, there has been like petabyte scale data per day, and you can easily process million records or so in a second. How much exactly depends, like what you're doing, how big your data is. It's hard to give like a general answer there. It does scale. I have to say that when we're running close to 1,000 nodes or something, I mean, that's a really high scale use case. There's some the job manager struggle. It does tend to struggle at that point of keeping communication with all the workers, and I think this has been like improved in newer versions of Flink, but there are even there are limitations with this parallel processing, especially when like a single master does all the communication and the bookkeeping.
That's a massive scale. Like I've worked on Kafka Streams, but it was nowhere close to this scale. So I can see how it can become like a bottleneck and how Flink can be used when it does. So with that, I have like a kind of a practical question, like based on the implementation or the applications of stream processing. So let's say I have like a stream of events, and I want to like enrich that stream with some additional data, and that data is not there, like available. So I have to make like a network call to, get that data from somewhere, and then, enrich that event and pass it on to like a sync topic. So is this like a good pattern for stream processing, or would you do like something like a join operation instead of like making a network call? So how do you see this this pattern?
Mm-hmm. Yeah, I've actually seen this pattern a lot, because if people, especially people who are new to stream processing, they tend to, run into this problem that they process some data, but now they need some kind of information from a database, or to I don't know. Let's say you process the user, some user event, but then you need to look up the actual user in the database somewhere, to confirm it's the right user ID or something like that. And then all of a sudden you have, let's say you have, hundreds of nodes that process data. Now you're spamming your database with, lookups for every event. And obviously that's not going to be efficient, because you're actually leaving the stream processing paradigm. You're doing, one record at a time, network call. You don't benefit from the optimization in stream processing. So that usually doesn't scale, or the database breaks down or something like that. So the more flinky way to do this would be to store the state in Flink itself, where it's actually needed. So that might be hard to do. I mean, it is tricky, because then your stream processor essentially becomes a database, right? And but that's like really a model that people follow. So the way this would work is, instead of looking it up every time, you would do it maybe once. You would do it once, and then store this user information in Flink itself. And because you have partitioning of the data according, let's say, to the user ID or some other key, you have that information stored in the worker that always processes that user ID. It's super efficient, because it's just in memory. And this state can grow, of course, very, very large. Let's say you have millions of users. So Flink has invested a great deal in having scalable state backends. So default one is in memory, which obviously has limitations, but there's also RocksDB state backend that is able to spill to disk and not require all the data to be always in memory. So that way, I mean, of course, whenever let's say you have a database that holds your source of truth, you run into problems, because then essentially you have the cache in this scenario. So what do you do if the data gets updated in the database? How often do you, this is a tricky problem, which depends on the use case. I guess you would maybe expire the state after some time and refresh it every 10 calls or whatever. You have to develop some strategies. But of course, from a Flink perspective, it's ideal if you just keep all state in Flink. And since Flink persists state regularly via its checkpointing mechanism, it is really like a database. I mean, you don't lose your state ever. But it has some operational challenges, of course, because now you might have your state in a database. You also have it in Flink. How do you transfer data between the two? How do you inspect the Flink state that it's actually correct? So the way this typically is done, I think, is that you treat all your changes as events. and those events go into the Kafka topic, and then this topic is read by Flink and some other process that writes to the database, or maybe even your Flink process writes to the database, so that you have a single source of truth, and that's usually Kafka. That way you don't have to actually do the lookup at all, because you have seen all the events that are also in the database.
Yeah, makes sense. So again, I think data locality is so important that you need to reduce the number of network calls or network shuffling that you're doing. So I think it boils down to that, right? So if that is the case, if you have to make network calls, so I've also seen cases when you don't really you're not allowed to store that data or that state locally because of some like compliance issue that this data needs to be in this domain. So in that case, it gets really tricky. So I have to make network calls. So I have to cache that data or that call somewhere that it is allowed. Otherwise, it's not going to work. So yeah, that's a very interesting challenge, I would say.
Yeah, there is one way to optimize this problem if you really need to call out. Then there's this so-called async operator in Flink, which is able to receive. Of course, it's going to be a bounded number of requests, but let's say you have a thread pool of 100 threads, and you can sort of run the DB calls in parallel, and still process or fetch the result at a later point in time. There is this feature, but it's not gonna solve all the problems, because you can only do so many requests at once. And at some point you have to stop the processing.
It becomes a bottleneck. I mean, you have to scale the database to have all those calls, or you have a bottleneck that you cannot scale your stream processing after a certain limit. So again, it's a trade-off, I would say. I think it makes sense. With this, let's talk about even harder problem when it comes to stream processing, which is exactly once processing. So it's been I guess Flink and Kafka Streams both have this semantics of you'll be able to process an event exactly once, and that's a really hard problem. So I wanted to ask you, why is it a hard problem, and how is Flink solving it?
Yeah, so exactly once processing is hard, because it means that you can only process an event once, right? And only once, exactly once. So in an ideal world where there are no failures due to broken machines or unreliable network, it's actually easy, right? You just read the data and you're good to go. But in the real world, you need to, to really do exactly once in all scenarios, you would have to persist your state after every event that you processed, because only then you would be sure to, at any point of time when there was a failure, you could go back to the previous record and just continue from there if you fail with the current. But it's a hard problem, because it's too costly to do that for every event. So what happens is that you Flink chooses an approach that it takes snapshots or checkpoints from time to time. So when there's a failure, we can roll back to the latest checkpoint and then start off from there. The problem with this is, of course, that's not exactly once, because then you're going to end up processing all the data again that you processed after the checkpoint was last made, right? In between last checkpoint and failure. So many systems talk about exactly once, and they sort of mean like their internal state. So from the process of Flink itself, it's really exactly once, because it never, like when you restore from a checkpoint, you will end up with the same result internally that then if you never failed. But from an outside perspective, from writing to, let's say, Kafka or a database, of course you're going to repeat that write, and that's really hard to solve in the general case. Flink has like a transactional sync support, so the way this works, it doesn't actually write to the sync until the checkpoint is completed. So you complete the checkpoint, then you do write out all the data, and that way you know that you're not gonna produce the records more than once. However, the outside system needs support for that, because what happens if you do the checkpoint, you write, but then you fail doing that, right? So you do it again. Well, no, that's not exactly once anymore, right? So the outside system needs to kind of know which transaction, essentially a transaction, has succeeded, and if you fail doing writing, then it needs to roll back. So it's Kafka has this transactional support, so Flink also supports it, but not all systems support that. So what users typically do to achieve exactly once is to rely on idempotent writes. And idempotent writes basically means that my output is first of all, it's deterministic. That's exactly once. That what is required by exactly once, or not strictly required by exactly once, but that's what I would expect if I roll back to an earlier point in time using a restoring from checkpoint. I would expect the same routes to be produced. Of course, there's some exceptions with like random number generators or so where that might not be the case, but for the general case, for most cases it is. And then when idempotency in writes means that when I write this result again, it won't actually change anything, right? It will just, let's say you have some ID for your record and a result, and your system knows that, I already received this ID, so don't do anything, or just write it again, but don't add it, as a new item because I've already seen it. That's kind of what idempotency means.
Yeah, I think it makes sense. And I think Kafka solves it almost in a similar manner. So they have like idempotent producers, and you have transactional producers, and then there is like different transaction isolation levels. So the consumer of the end topic or the sync needs to read only committed messages. Otherwise, it will see like duplicate or duplicate events. So I would say there is some confusion around exactly once processing. It's not exactly once delivery, but it's rather the side effect of that processing is exactly once, right?
Yes, that's what people typically mean. I think.
Yeah.
That you have effectively exactly once. How you achieve that via transactions or via idempotent writes, that's depends on the application.
Yeah, and with these transactions, definitely there's going to be like cost involved in terms of latency, because you're having like transactions and you need to make a lot of like checks here and there. So definitely adds more latency. So I think the best approach is to not guarantee exactly once, and deal with at least once guarantees wherever possible. And I think maybe more than 90% of the cases can survive with like at least once guarantees and not exactly once. But there are some like mission critical systems that we want to design where exactly once processing is required. So I think Flink and Kafka, I think both are suitable for that. With good enough trade-offs.
Exactly. Yeah.
Yeah. Yeah, sounds good. Sounds good to me. Just one last thing before we, end this amazing conversation is like, how do we test all these things? Like, if we have like a stream processing pipeline, and I have to run it in production, so I have to make sure that all the functions and all the joins that I'm doing or all the transformations I'm doing, it's actually correct. So definitely I can write some unit tests, but is it enough, or what is the general pattern of testing these like stream processors?
Mm-hmm. So I guess you refer to testing like user pipelines written for the system, right? Yeah. So as I mentioned, Flink has this like local execution mode, which starts all the actual components locally on your computer. So you can write sort of unit tests, or sure if they're still unit tests, they're more like integration end-to-end tests actually. You can write, so you of course you might not have your actual data available, like your Kafka topic or whatever, but you can generate some example data and then run through the processing, test all your operators, and get the result back and verify that it's what you expect it to be. So that's typically how people sort of rudimentary test their application or their pipelines. But then, of course, you might have some more sophisticated CI, CI integrations where, you bring up an actual cluster of all dependencies and you run on some example data that you have, so that you can see that it works on an actual Flink cluster. And with all the dependencies that you need during production. So I think and then you can of course write unit tests for your individual operators if you have any custom operators that do more complicated things. You can test those. Flink has some test utilities for that, to even test restoring from state and verifying that state gets updated as expected.
Yeah.
So I think these are typically what people use when they write it. Yeah. How's it for Kafka Streams?
Yeah, I mean, so for fault tolerance, instead of checkpointing, or maybe we can call it checkpointing, but there's like another Kafka topic where Kafka captures all the change log, so it can recover if something fails while performing the stream processing. And then there is also RocksDB for the state or the tables, as they call it, for storing the exact like external state. And they can also have like APIs on top of it, so you can expose that external state to like external users. So the way I have seen it is, you just test your pipeline and then you verify that the external state is correct and the changelog topic had, the correct events and so on. So I think it's just about just running the stream and then checking all the state is supposed to be, is correct basically.
Yeah. Right. So yeah, in an end-to-end test scenario, you probably want to, let's say you have a reading from Kafka and you're writing to some database. You want to insert those events into Kafka, wait until the processing is finished, and then verify the result in your database or so. So
exactly.
Yeah, that would be.
It's just that like sometimes I've seen these tests to be like flaky and they might just fail because some other issue. It's not really an issue with stream processing, but after all, it's a distributed system and there can be like hundreds of moving parts, so hundreds of issues. So yeah, I think that pattern makes sense, that you can test like end-to-end stream processing.
I think if you like devote enough time to unit test your operators and then ensure that your Flink job is actually doing what you want, then these like end-to-end tests are very useful for checking that. I mean that the configuration is correct, so you can actually read and write to these systems, and it sort of gives a little bit more confidence for sure. But if you do all the work before, I think that's probably more critical, because sometimes there are misunderstandings on how state works, how time is handled in Flink, and if you invest more time upfront in a unit test and integration test level, then you end up, I guess, solving the hard problems.
Yeah, I think so. I've also experienced that. Like, spend more time in unit testing, and then ultimately the entire thing will work together nicely, instead of like spending a lot of time on hard problems. So, yeah, I agree. Great. So, I think it was such an insightful discussion. I think you cleared up a lot of confusion on like stream processing versus batch processing, why it might not be the best thing to compare, and like why it is more relevant in this like time, and why companies are moving to stream processing, and how like different tools are compared. So I think it was really insightful for me, and it was a nice conversation. I really enjoyed it. So thanks a lot. Thanks a lot for joining me and answering all my questions. And looking forward to collaborate with you more.
Thank you, KV. Yeah, it was great chatting with you. I think we managed to talk about a lot of topics. There's still a lot, but actually many other things that came to my mind throughout. We could definitely jump on another podcast, let's say, to discuss more differences between Flink and Spark, or event time versus processing time, and how windowing works or something like that. But this has been, I think, a good overview, and curious to do it again soon.
Awesome. Yeah, looking forward to it. Thanks a lot.
All right, thanks, KV.